Dear viewers, I would like to welcome you into another interesting and fun maths and fact video. Before to proceed further, I will request you to kindly subscribe and share this channel with your peers so that they will be enjoying the same facts that we are going to demonstrate today. So today's video is related to a theorem called the Fermat's Last Theorem. That theorem was proposed by or given by a French mathematician called Paris de Fermat in 1637. In the textbook of the mathematics, this theorem is also sometimes referred as a conjecture. Although conjecture and theorem are two different segments, because in 1637 when Fermat proposed this theorem, he didn't give his proof. And he said that in his interesting way, this is in fact the fact that we want to discuss as well, that the proof of this theorem is too large that it cannot be held in the margins of the journal. Journal known at that time was Arithmetica. Yes, that's true. This is the interesting part, that the theorem was not given as a proof because the margins of the margin of the journal is not enough to hold the proof. That was he proposed in 1637, and it was accepted by the mathematicians as well at that time, because whatever be the theorem statement is, which will obviously I will give you in later stage, is true, but there is no proof. So sometimes that refers as a conjecture, a Fermat conjecture as well. However, that conjecture remains till 1995. In 1995, a British mathematician, Andrew Wills, proved that theorem by using a modular classical theories, which we are not interested at well, because we want to make this theorem easy to understand by the everyone. So does not need to be expert in the field of mathematics. So in 1995, British mathematician Andrew Will gave his proof in a series of proof. In fact, he made some mistake in his proof as well. Then he corrected in 1994 to 1995. However, in 1995, he will be awarded the correct proof. He has given the correct proof. In 2016, he was awarded as well with the prize, Nobel Prize. So let's dive into the main part, that what is this theorem is, and then I will discuss what are the limitations of the theorem. So to understand that theorem, let's assume a graphical approach. So let's assume I have a three cubes. A rectangular body that have equal dimensions. What this means? It means that it's every cube has the same length, breadth, and height. So this is a cube 1, cube 2, cube 3. So for example, the cube 1 has a length A, sorry for that, has a length A, height also A, and A could be measured in any unit, centimeter, kilometer, and breadth is also A. Similarly, the cube B, cube number 2 in fact, has a dimension B, length B, height also B, and the breadth is also some number B. And similarly, there is another cube which has a dimension C in each side. So length C, height C, and breadth is also C. So if I ask you a simple question, that what would be the volume of the cube 1? So your answer is quite simple from the early geometrical concept that the volume, that is the quantity that this cube can hold, is equal to the length multiplied by its breadth and then multiplied by height. So in this case all are small a. So I can write the volume of the cube 1 is a cube, that is a multiplied by a multiplied by a. Similarly, if I ask you that what is the volume of the cube 2, then your answer is quite similar, that is b cube, that is length b multiplied by breadth b multiplied by height b. Similarly, if I ask you that what is the volume of the cube 3, then your answer is c cube. So that's very easy. So what the Fermat last theorem has to do with this? So if I ask you that what is the total volume of cube 1 and cube 2, so your answer is quite clear. You say add the volume of cube 1, that is a cube, into volume of cube b, that is this part, which means you just need to add the volume of this part and the volume of this cube. So that gives the total volume of cube 1 and cube 2, which is represented as a cube plus b cube. Now, if I ask you, can you form a cube which has a dimension c such that the volume of cube 1 and cube 2, that is the sum of the volume of cube 1 and cube 2, is equal to the volume of the third cube, that is the cube that has a dimension c. So is it possible to find a cube, third cube, that has a dimension c? So think about it. You can pause the video here and think about it. Can you give an example? As so far you can give example, but the point is that these dimensions that I have told you does not have any condition at the moment. So let's dive a little bit more. So if I say you have to find a dimension c such that whatever be the quantity, that is the volume of this cube, has to be equal to the volume of the individual cubes, that is a cube plus b cube. But the condition is that a, b and c must be a positive integer, and as I already called them A, B, C, so you can clearly understand they have to be distinct as well. There is not A and B and C are all three different numbers. So A, B and C must be a positive integer. What does this mean? Any number that can be that have no fraction part. In short, a decimal. It does not contain decimal. So what are those numbers? Positive means greater than 0 and they should not have a decimal. So number may be 1, 2, 3, 4, 5 and so on. Set of natural numbers you can say as well. So this is the condition of the case. Now think again about this problem. So can you give me a three numbers A, B, C that are positive integer that solve this problem? That is, the dimension of the cube 1 is A and dimension of the cube 2 is B. Then the volume of the cube A plus cube B must be equal to the dimension of the volume of the cube C, cube 3. So you have to find a dimension C such that. So here comes the Fermat Last Theorem. Fermat says that if A, B, C are three positive numbers, positive integers, then you cannot solve this problem. Although this is not the statement, has nothing to do with the cube, but I explain it like that. So in this case, you cannot find three numbers a, b, c, which has to be a positive integer, that solve this problem. In other words, if these two are the cubes and total volume enclosed by these cubes are a cube plus b cube, then it is not possible to find another cube that has the volume equal to these sum of these two cubes, provided that the dimension of each cube is a positive integer. That's the fact. So what does exactly Fermat theorem says? Fermat Last Theorem says that for any any three yes, any three positive integers, let's say a, b, c, you cannot satisfy following equation. The equation is a raised to the power n, I will explain this n, plus b raised to the power n equal to c raised to the power n. That is, you cannot find three numbers a, b, c that will be raised to the power n and sum together is equal to c raised to the power n, where for all, this is a symbol called for all, n greater than 2. For all n greater than 2. Now the question is, the example that I give you, how can we relate these two things? So for n, in the previous example, the n is 3 because we want to find the cube. So cube is 3, n is 3. So it is greater than 2. And I have a condition later on that ABC must be a positive integer, which means that I cannot solve this problem based on the Fermat Last Theorem. That is, I cannot construct a cube that can hold the same volume as the two individual cubes, provided that the dimension of the each cube is a positive integer. So I hope you like the fact that I have shared with you today. So this is just a short video about the Fermat Last Theorem. And the interesting part that I like about this theorem, in 1637 he gave a proof and he said that the proof of this theorem is too large. Sorry, I cannot give it in a journal. A margin of journal is not enough. But they accepted that proof. So I suggest all of you, especially the students that are following, do not do it in the 20th century. If you do it in your exam and write down in answer script that I know the answer, but the answer is too lengthy to write down in the answer script, you will get 0. So I hope you have followed my advice. Thank you for your time. This is just a one fun fact mathematics video for your entertainment.